Alright, so in this video we're going to talk about some other particular little things about gases, mainly their speed, and also how gases don't always behave in the way that we imagine that they should behave. So in ideal situations, gases will behave in certain ways, but that doesn't always happen. So at high pressures and low temperatures, some parts of kinetic molecular theory, which is how gases should behave in ideal situations, are invalid. So one thing is that KMT says that volume of gases are negligible. And technically, yes, a gas will take up some space. It just takes up a very, very small amount of space compared to the container that you put it in usually. So we usually say that the volume of the gas is actually negligible. That's not always true. So when you have a gas and you pressurize it into a small space, like you push it closer and closer together, that space that it occupies actually becomes much more significant. So the particles do actually occupy some space. Another part of KMT, kinetic molecular theory, is that the forces of attraction are negligible. So you've got these gas particles are moving all over the place. They're not attracted to each other. They're not repelling each other. That's not always going to be the case. If you have a low temperature, that means less energy is going into those molecules. Those particles are actually going to be closer together, and because they're closer together than they normally would be, you're going to have some sort of forces of attraction or repulsion happening. All right, so real gases, the volume is a little bit larger than it should be. Okay, and so if you're calculating the volume, your volume might actually be larger than what you calculate it should be. Okay, so you would actually have to subtract out a factor to get the real volume, what it should actually be. Pressure will be lower. Okay, that's because those molecules are closer together, so those forces of attraction are actually pulling those molecules even closer together. So they're not colliding with the container as often. So if you were to calculate a pressure and there's some attractive forces between those molecules, you're actually going to see that the pressure is lower than what you would calculate. So if you were doing this and you were trying to get a more accurate calculation, you would have to add in a factor. So this equation, really, this is the ideal gas law combined with van der Waals equation. You will not have to do anything with this, okay? What you do need to know is how the volume and the pressure can be different under this situation. So if you are looking at a gas, okay, and at a low temperature and a high pressure, your volume is going to be larger than it should be. So if you go calculate the volume out, and if it's at a high pressure and a low temperature, you're actually going to notice that the volume is larger than what you actually calculated out. Pressure will be lower than the calculations say. And that's because the molecules, since they're exhibiting some forces of attraction to each other, they're closer together. They're not going to be colliding with the container as much, so the pressure will be lower. So this is the gist of it. Okay, under high pressure situations, so when you put the gas into a highly pressurized container and you have it at a very low temperature, the volume is going to be larger than it should be, and the pressure will be a little bit lower than it should be. All right, so the velocity of the gases is related to a couple of different things. It's related to mass of the gas and also the temperature. So U is the velocity of your gas, and you can calculate it with this equation. So you use 3 times R, and the R here is going to be this, okay? And you multiply that by the temperature in Kelvin divided by my molar mass. You're going to have this in kilograms. The molar mass will actually be in kilograms because when you look at this unit right here, the joule is actually this. Okay, so this is what a joule actually is. it's a kilogram times meter squared divided by second squared. So that's why your molar mass has to be in kilograms, and that's the reason. All right, so let's find the RMS, the root mean square speed of a chlorine gas. So that's just a fancy way of saying how fast is the gas going. So let's find the root mean square of the gas. So we know that speed is equal to this. All right, so let's see what else was given to us. So we were given a temperature in Celsius. So let's go ahead and convert that. We're dealing with gases. It has to be in Kelvin. So 80 plus 273 gives me 353. I know it's chlorine gas. Chlorine gas is a Brinkelhoff, which means it's diatomic. So the molar mass of Cl2 is 70 grams per mole. Well, I know because of the R here, I'm going to have to convert this to kilograms. All right, so kilograms. So 1 kilogram is equal to 1,000 grams. Okay, so you're going to get 0.07 kilograms per mole here. All right, so now I've got my temperature, I've got my molar mass, I have my constant. I can just simply plug it into the equation. All right, so 3 multiplied by 8.314 times 353 divided by 0.07. So 3 times 8.314 times 353. All right, so divide it out. You're going to get a very large number, but remember you need to take the square root. Don't forget to do that part. All right, so now you're going to get a speed that is equivalent to this. 354 meters per second. And then that's actually an okay speed for gas. So your chlorine gas is going to have a speed of about this, using that equation. All right, so now let's look at something different. Because more than likely you're going to be asked conceptual questions, not mathematical questions about the speed of gases. So here's a graph, and the graph here has number of particles on the y-axis and then the speed on the x-axis. So you go from a slow speed to a fast speed here, and what you have here is you have various gases, so you have different gases for each line at the same temperature and pressure. So you need to figure out which gas would be which gas. So we're going to compare the molecular mass. Okay, so the molecular mass, the larger it is, the slower your speed is. So this, if you have a large gas, it's going to move very slowly, and that kind of makes sense. It's intuitive. So the larger gas, the lower the speed. So we need to figure out which of these three gases is going to represent the heaviest, and then which is going to represent the lightest molecules. All right, so what you have here, why it looks like this, is it's giving an average for all of your particles, what their speeds are. So it's the root mean square. So that's why we have this hump right there. So we're looking at like basically the height or the maximum point of each little peak. All right, so we need to figure out which one will be the heaviest and which one will be the lightest. So remember, here in the x-axis we have speed. Well, the faster speed is over here. So the hump right here, the maximum point that has the fastest speed is this one. The one that has the slowest speed is this larger hump right here. So that means that the more massive gas is going to be this one right here because it's slower, and then the least massive gas is going to be right here. So it's going to be a lighter gas right there. All right, so let's look at this question. So which substance is going to move at a higher velocity at the same temperature. So you've got four gases that they're comparing. Carbon dioxide is about 44 grams per mole. This one's about 131. Oxygen gas is about 32 grams per mole, and then helium is 2 grams per mole. So when I look at this and I'm comparing these values, the fastest gas is going to be the lightest gas. So in this case, it's going to be helium. All right, so now which gas would have a higher amount of kinetic energy? All right, so and this is at 273 Kelvin. Well, we know that this one would have the highest speed. Okay, so when we're comparing speed is this. So the more mass of the gas, the slower the speed. Well, kinetic energy is equal to this. Okay, this is kinetic energy. But the thing is, you've got mass and velocity here. Well, you know if your mass changes, your velocity is going to change as well. Your kinetic energy is not going to be impacted by the molar mass. So this is actually it's a trick question. The gases are all going to have the same amount of kinetic energy because they're at the same temperature. And so the mass does not impact kinetic energy, it impacts speed. So the kinetic energy really depends on the temperature. All right, so let's look at something with temperature and speed. All right, so when I look at this equation right here, M is on the bottom of the equation. So if I have a bigger m, that's going to equal a smaller number here. So if you have a more massive gas, you have a slower gas. Since that value is under a square root sign, you have to take the square root of that factor to figure out what happens with the speed. So basically, if you know that your gas is 4 times as massive, so I have a gas that's 4 times as massive as something else. So I have the speed of some gas, and then I'm comparing it to another gas, and the gas is 4 times the mass of the other. Well, I know that that means that the speed is going to decrease. So if I'm if I'm trying to figure out how much faster or how much slower the gas is going to be, I need to take this factor and then take the square root of it because it's under a square root sign. So if I take the square root of 4, I get 2. That means that the gas speed would go down by a factor of 2. So if you're given a question where it says arbitrarily, you have a gas, you're comparing the gases, one is 4 times as massive as the other one, what can you say about the speed? Well, you can figure out that the speed would be half the amount of the other gas. Okay, so let's look at another kind of example. Let's look at temperature. Okay, so temperature here, since it's being multiplied in my equation, I know that the higher the temperature, the higher the speed. So if I have a higher temperature here, I'm going to have a higher speed. So that's going to lead to an increase in U. Well, if I look here, it's also being square, there's a square root sign over it. So that means if my gas, or if my temperature was 4 times as great as a different temperature, well, I know my velocity would go up, but let's say that's 4 times as great. I'm going to take 4, take the square root of that, and then I could say that the speed would be twice that than the other speed. All right, so let's look at this. So in this case, I have various temperatures here. So it's the same graph. It's just now I have the same gas. So the three peaks represent the three gases, but just at different temperatures. So I want to figure out which one is at the highest temperature and which one is at the lower temperature. Well, I know that if I increase my temperature, I'm going to increase my speed. So I know that this peak right here is going to be moving faster than the other two gases at whatever temperature they're at. So I could say this peak represents the gas that is, it's the fastest one, so it's at the highest temperature. This one is the slowest gas, so it's at the coldest temperature. All right, so Graham's law deals with effusion and diffusion. So effusion is when the gas particles escape a tiny hole. So you have like an aerosol container and you're spraying gas molecules out of it. So this is different than when we talk about speed. So when we talk about speed, we're talking about how fast they're moving in general. But when we're talking about effusion, we can talk about a rate of escape. So how fast can the molecules escape? It's not the same thing as speed, because when we talk about speed, we don't really think about collisions that happen. And there's going to be a lot more collisions happening when it escapes through a tiny little hole. Diffusion is when your particles move from an area of high concentration to low concentration. So basically, if you spray a perfume, it's going to be a very concentrated smell where you sprayed it and less concentrated everywhere else. Well, eventually, those gas molecules will start moving out, and then everybody will smell it eventually. Okay, so this is Graham's law right here. You probably will not have to do any kind of calculations with it, but I'm going to show you how to do the calculations. And basically, you compare two different substances, and you're going to compare the molar masses. So the more mass of the gas, the lower the rate of effusion. This is not the same thing as speed, though, because we have to deal with collisions. Okay? You can also look at density. So you can look at molar mass here, or you can look at density. Okay, so the more mass of the molecule, the slower the rate is. The less massive, the faster the rate will be. All right, so let's compare ammonia to carbon dioxide. All right, so if I'm looking for a rate, just a single rate comparing two different gases, that's going to be a single number. So really, this is what we're looking at. So I know in the equation that we just saw, so let's go back, that we saw two numbers. But if I'm just looking for a rate, I'm really just looking for one number. I'm looking to say whether it's like 3 times as fast, twice as fast, or maybe I'll say that it's 0.25 of the other gas. Okay? So you're looking for a single number if you're just looking for a rate. Okay? All right, so I can compare the molar masses of these two gases. Ammonia is NH3, and its molar mass is 17 grams per mole. Carbon dioxide is 44 grams per mole. So I will just simply plug it in. So R is equal to this, and typically what I do is I like to keep the more massive gas on the top. So M2, I'm going to say, is the more massive gas, or carbon dioxide, because I know carbon dioxide should have a slower rate than ammonia. All right, so now when I do this, let's say 44 divided by 17 gives me 2.58. Don't forget to take the square root, though. Okay, so 1.6. So I'm just looking for a single number here. I'm not looking for two different numbers. I'm just looking for 1.6. So basically what this means is that the faster gas effuses at a rate of 1.6 to the other. So basically the faster gas will be ammonia. Okay, so 1.6 times as fast. So, or faster. So basically what this means, I know that ammonia will be the faster gas. are the one that effuses at a higher rate. So ammonia is 1.6 times faster. And ammonia is going to move at a faster rate because carbon dioxide is more massive. Okay, so if your rate is larger than 1, the gas is faster. If it happens to be less than 1, then that is the more massive gas. It's moving slower, okay? So a rate that is more than 1, it's faster. Less than 1, it's slower. And if it's slower, that's the more massive gas. All right, so let's look at this. All right, so if gas A effuses at a rate that is 0.25 times that of gas B, what can be said about the mass of the molecules? Okay, so this is one of those questions where you just kind of have to think about it. So we know that gas A is being compared to gas B. Gas A effuses at a rate that is 0.25 times that of this. So if it's less than 1, so it's less than 1, that means that it's slower. Okay, so gas A is slower. So if it's slower, I know that it has a bigger mass. Okay, so I know the mass here is smaller. So I know if this one is 0.25 times of this gas, it moves a quarter of the speed that gas B does. So this is 1/4. It moves at 1/4 the speed that gas B does. So that means that gas B moves 4 times as fast, or has a rate that is 4 times higher. So if I know that this one is 4 times higher, I can kind of figure out a little bit more about the mass. I know that gas A has to be bigger. I know gas B has to be smaller. But if I know that gas B is 4 times higher, like the rate is 4 times higher, that means that this mass, which will be the heavier mass, will be greater than this one. But remember, I can't just say it's 4 times as great because of the square root sign. So what is the square? 4 is equal to the square root of what? Well, 16. So that means that mass, or gas A, has to be 16 times more massive. And then what you have to do is you have to think about this. They have a square root sign right here. So once you figure out how many times bigger this is, you would take the square root of that number to get your rate. Well, if I had 4 times the mass, so let's say this mass is 4 times the mass of this one, well, I have to take the square root of that. The square root of 4 would be 2. So it cannot be that the mass is only 4 times as great. It has to be that it's 16 times more massive. So whatever the mass is here, it's going to be 16 times that of the other gas right here, which is gas B, or gas A. It's just one of those questions you kind of just have to think about.